All right, so in this video, what we're going to do is we're going to look at the Gram-Schmidt process, and we're going to take a basis for a subspace, which is not already orthogonal, and convert it to an orthogonal basis for the subspace. Now, one thing to kind of keep in mind about this is that you can extend this process for any dimensional space, but the more vectors that you have to do this for, the messier the numbers tend to get. So you kind of needed to do it to see the algorithm at work. You kind of need to do it for at least 3 vectors, because essentially what this does is in the first step, you project onto a single vector. And then in the second step, you project onto a subspace formed by the first 2 vectors. And then in the next step, you would, if you had a fourth vector, you would need to project onto a subspace that has 3 vectors. And so this is where things can start getting messy. So the third 3 vectors is usually enough to, again, kind of get a feel for how the algorithm is going to develop, but it becomes computationally more and more expensive to keep adding additional vectors to the space. So the algorithm works fine, it can continue. It's just for people, particularly when you're a student doing an exam and you don't have a lot of time, time pressure. Sometimes the vectors can get really messy, and if you make an arithmetic mistake, they can get even messier. So we're going to work through an example with 3 vectors because I think this is enough to see how the procedure would flow, but not so much that things start getting really hairy. But you can end up with some pretty nasty looking vectors, even with 3 vectors, if you are not really being super careful about what those vectors end up looking like. And I haven't been particularly careful, so we'll see what happens when we get to that third step. All right, so we're going to start with the vector in my example that has the most zeros, to hopefully that will keep things from getting crazier than they absolutely need to. Now, what we're going to essentially say, let's say we have, call these V1, V2, and V3, and maybe in our original vectors. And essentially, the first step is just to take the first vector, V1, and we're going to designate it to be the first vector in our new vector space. The first basis vector. So V1 is B1. There's no restrictions on what this vector can be because there's no other vectors in the set. And so for right now, that's super easy. But now we want to make sure that the second vector we put in the set is orthogonal to the first one. And so to do that, we're going to need to project the second vector onto the first vector and then calculate the orthogonal complement in order to extract the perpendicular component of the second vector, so that the 2 vectors that we're left with are the original, they're orthogonal to each other, but they still span the space that the first 2 vectors spanned. So essentially what we're going to say is B2 is going to be V2 minus the projection onto V1 of V2. And one way that you could think about this, V1 is B1. This is the same thing as projecting onto B1. All right, so let's calculate the projection of V1, of V2 onto V1. So recall the projection formula. It's V1 dotted with V2 divided by, we're projecting onto V1, so it is V1 magnitude squared, and then times the original V1 vector. So if we do our dot product, we're dotting these 2 together. So 1 and 1 and 0 and 1, and 3 and 1, and 0 and 1. And then in the denominator, squaring everything, 1, and then adding them up, 1 plus 0 plus 9 plus 0, and then times our original vector. And again, we'll put parentheses around us to remind us that this is a constant and this is a vector, and we're going to end up with 4 over 10 or 2 over 5. And so if we multiply those out, we're going to get 2 over 5, 0, 6 over 5, and 0. And then we're going to calculate B2, which is going to be the original V2 vector minus our projection onto the first vector. And so 1 minus 2/5 is going to give me 3/5. And then 1 minus 0 is 1. And then 1 minus 6/5 is going to be negative 1/5. And then 1 minus 0 is 1. Now, because we are forming a basis, we can now rescale to eliminate fractions in the basis. So we're going to actually make B2 equal to 3, 5, negative 1, 5. One too many components. There we go. So now we have two vectors. We have our original 1, 0, 3, 0, and we have this vector as now two vectors which are orthogonal to each other. And let's double check. If we project, if we do the dot product between them, 1 times 3 is 3, 0 times 5 is 0, 3 times negative 1 is negative 3, 0 times 5 is also 0. So 3 and negative 3, add them up, you get 0. So they are orthogonal to each other. And now they are forming, again, a partial orthogonal basis for the other, for the subspace. And now we need to apply the same process, but with two basis vectors to the third vector. So now B3 is going to be V3 minus the projection onto B1 of V3 and minus the projection onto B2 of V3. So that, again, now we have a subspace that has an orthogonal basis, but it's only two-dimensional, and we need to project onto the subspace in order to take out any part of V3 which is already in the subspace in order to get an orthogonal vector that's perpendicular to the subspace and extend our orthogonal basis to the original span. So there's a bunch of projections we have to calculate here. So let's start with the projection onto B1 of V3. And again, we'll copy our formula and update our subscripts. We're going to project, again, onto V1, and B1 are the same thing, but we'll just update the notation just so that we're consistent, because we can't use V2 in the next go round. We have to use B2. So projecting onto B1, and then V3 only appears one time. So let's try this. So if we dot B1, which was the this one with this vector, we're going to get 2 plus 0 go back, 2 plus 0 plus 12 plus 0. And then in the denominator, it's 1 plus 0 plus 9 plus 0. And then we're going to multiply that by our B1 vector, which was this guy. And if we simplify, we get 14 over 10, which is going to be 7 over 5, or 7 over 5 and 0 and 21 over 5 and 0. And then we're going to do the same thing, but now with B2. So we'll change that subscript, and we'll change that subscript, and that subscript, and that subscript. And so we're going to end up with B2 was our 3, 5, negative 1, 5. And we're going to dot that with the 2, 3, 4, 1 vector. So 3 times 2 is 6. And then 3 times 5 is 15. And then negative 1 times 4 is negative 4. And then 5 times 1 is 5. And then our B2 vector, we have to put a bunch of stuff in the denominator, so we have to square everything. So 9 plus 25 plus 1 plus 25. Now again, one of the reasons we rescaled this vector was because if you don't, your denominator is going to have a bunch of fractions in it. So we would have had 3 over 5 squared and 1 squared, and then 1 over 5, negative 1 over 5 squared. It would not have been any better. So yes, we have some large numbers here, but at least they're not fractions. So 6 plus 15 minus 4 plus 5 is going to be 22. And our denominator, 9 plus 25 plus 1 plus 25 is 60. And so we can reduce that, not by very much, to 11 over 30. And if we multiply, we're going to get 33 over 30 and 55 over 30 and negative 11 over 30 and 55 over 30. And then to get our third vector, we're going to take V3 minus these projections. So V3 was our 2, 3, 4, 1 vector, and we're going to subtract off this vector and this vector. All right, so let's see what happens. 2 minus 7 divided by 5 minus 33 divided by 30. It's 1.7, which is going to be 17 over 10. And then we're going to take 3 minus 0 minus 55 divided by 30. And that's going to give us 7 divided by 6. And if I take 4 minus 21 divided by 5, and I subtract negative 11 over 30, I'm going to get 1/6. And finally, I take 1 minus 0 minus 55 divided by 30. And I get negative 5 over 6. And again, I can rescale this so that I can get a vector that has just relatively small integers in it, because those are the easiest to work with. And I can do that because it's the basis and not the orthogonal complement necessarily. So the common denominator appears to be 30. So if you're doing the arithmetic by hand, don't feel like you need to reduce the vectors. I used a calculator to get the reduced fractions, but you don't need to reduce them. You can leave your denominators at 30, and then this will be a lot easier. So 17 divided by 10 times 30 is going to give me 51. And then 7 divided by 6 times 30 is going to give me 35. And 1 divided by 6 times 30 is obviously going to give me 5. And then negative 5 divided by 6 times 30 is going to give me negative 25. And I should be able to see that this vector is orthogonal to my other vectors. So let's put them all together and see. The span was my original 1, 0, 3, 0 vector. And then my second vector was this guy. And then my third vector is this guy. And you can see these numbers being as crazy as they are, that of course, if you were to extend this into a fourth vector, the coefficient would get even crazier. And, so this is a common thing that happens when you do Gram-Schmidt. So let's just double check. So let's say I want to dot these two vectors together and hope that things work out. Maybe I have an arithmetic mistake someplace. But let's double check. So we double check these, 3 and minus 3. That's good. So let's try, this looks like 51 and 15, and that doesn't seem like that's going to work. So let's see if we can figure out where the sign error was. So let's go back to my subtraction. Let's start there. 2 minus 7 divided by 5 minus 33 over 30. There's my mistake. That should be not 17 over 10. That should be negative 1/2. And that will make a lot more sense. If I multiply, now my common denominator is actually 6. So let's rescale this. Multiplying by 6, that's going to give me negative 3. And multiplying this by 6 is going to give me 7. And this by 6 is going to give me 1. And this by 6 is going to give me negative 5. Fantastic. So this vector, those are much smaller numbers. And see, again, this is another good reason why you check the dot product to make sure everything is in fact going to be 0, because that's how you know whether or not you've made an arithmetic mistake. And it's a fairly simple catch. So 1 times negative 3 is negative 3. 3 times 1 is 3. That's 0. The other two components are 0. So B1 dotted with B3 works. So now let's try the other one. 3 times -3 is -9. 5 times 7 is 35. 1 and -1 is -1, and 5 and -5 is -25. And if you add all of those up, you do get 0. -9 and -1 is -10. Add that to -25, you get -35, which cancels out the 35 in the second component. So checking the orthogonality, you do in fact get an orthogonal basis if you don't make any arithmetic mistakes.